I mean, this is the simplest and most straightforward step that you can do for model interpretation. And it tells us the most impactful features that are learned by our model. So most of the times, it's sufficient to take a small set of samples from the data set for model interpretation. This is like, I mean, there are two advantages to it. One is that you can train your model faster, and the second thing is you don't overfit to your data. And so generally, what we usually what is usually done is you try to build a random forest model as quickly as possible on your data set. It doesn't have to be the best model, but of course it has to be better than random. Uh, but but yeah, you just like train a random forest model as quickly as possible, and then get to the and then plot out the feature importance values. So in this case, you can see I'm using the random forest regressor from scikit-learn. I've specified the number of trees, the number of minimum number of leaves that should be samples that should be there in the leaf node, the maximum number of features that each split can use, and here are the values. These are the RMSE values on the training and validation set, and here are the R squared values. So we have reached a pretty decent accuracy here. And now if you look at the feature importance of our features, let's get straight to the plot here. You can see that the feature year made, which basically says when the equipment was made, like the year in which the equipment was made, is the most impactful feature. There are some other features as well, like coupler system, product size, uh, which we'll analyze like later. Uh, and also, you can see that this graph develops like a tail. Uh, I mean, the values kind of start to diminish once we reach these areas. So um, we'll just select the most important features. And after doing that, we kind of restrict our features to 25 and then retrain our model on these 25 features. And you can see that after discarding those features, we almost have the same RMSE and R squared values. So this basically tells that those were redundant columns, and removing them will not make our model worse. And if in fact it makes our model worse, then those are not redundant features. So now again, if we plot our feature importance plot, it looks pretty similar to the one that we obtained earlier. Uh, Now, yeah, I'd also like to point out that removing redundant features also helps in removing sources of collinearity. Uh, uh, so, so yeah, I mean, we'll discuss about it a bit later. Now, feature importance is generally a very generic method that you can actually use for any model. It doesn't have to be a random forest or you know, or a regression or a linear regression model. It can even be a neural network. So I'll give you a basic the intuition behind how this is calculated. So basically, let's say this is our data set, uh, and these are the columns, which are the features. Price is our target variable, and these are the rest of the columns are features. So let's say I want to calculate the feature importance of the feature year made. So what I'll do is I'll randomly shuffle the contents of the column of year made. So what this will do is it will preserve the statistics of this column, right? I mean, the mean will remain the same, the standard deviation will remain the same, but what we are doing here is we are breaking the relationship between the feature year made and the price, that the thing that we are trying to predict. So what the next thing I'll do is I'll pass it through the random forest and make an inference. I'll get the predictions, and after getting the predictions, so let's say now I get an R squared of before shuffling, before when the data was as like in its original form, the R squared was say 0.9, and now after shuffling the year made column, I'm getting an R squared value of 0.8. So it basically tells me that how important this feature is towards the prediction. So in this case, you can say that it has a feature importance of 0.1, but I mean, it's exactly not the same. I think it's calculated a little in a different way, but you can obviously use this kind of intuition in like in different for any kind of model. And and similarly, you can do the same thing with the rest of the columns. Um, so let's say you can you can you can make the year made column back to how it was like in the original data set, and then shuffle the enclosure column, and then pass it to the random forest, and then see the predictions and find its feature importance. Now you might be tempted to ask that why not just restrict the feature set and remove one of the columns one by one and train your random forest and find the R squared. Well, that would also work, but the limitation in that case is that you'll have to retrain your random forest again and again. Well, in this case, you're just using your random forest for inferencing, which is pretty fast. So that's the advantage of doing finding feature importance using this technique. Uh, Next, I'd like to touch upon another important thing, like on one hot encoding. So basically, one hot encoding is usually used for categorical variables. So let's say we have a feature that has these subcategories. It has a mid value, it has a low value, and a high value. And then there are some values which are unknown, which are represented here as NA or not, which is not applicable. So what one hot encoding does is it creates a column for every subcategory. So basically, so from one feature, you now go to 4 features in this example, and and you populate uh, populate everything with zeros except the cell in which uh, except the cell in which that column is active. So here you can see that when so let's say this is row 0. So in row 0, since we have feature mid active, so you just mark 1 at mid and set the rest of them as 0. So what it does is it helps you to analyze the subcategories and the relationship with the target variable, which in this case is price. And of course this can lead to some problems sometimes. So you'll have to choose this analysis based on how many categories you have per feature. So here, since there are only 4 categories, you can easily like create one hot vectors for you can easily create 4 extra columns. But in cases, but this obviously won't work when there are a lot of categories. It will lead to a high dimensional problem, and which like machine learning models have a hard time to they have a hard time dealing with high dimensional problems. So you have to be careful regarding that. So once I encode this as categorical features and retrain them, I see that the performance has slightly decreased a little bit, but and we'll see. So I did this only to like in the later part of this tutorial, I'll show you how we can do some analysis with categorical features. And in the feature importance plot, you can see that this category enclosure EROPS with AC, it turned out to be the most important feature that's affecting the price. So we'll do a little bit of analysis, like what this feature is, and see if how one hot encoding helps. Now next, let's look at something called dendrograms. Uh, Now dendrograms are very similar to hierarchical clustering. So if you know about hierarchical clustering, what you do is it's kind of a unsupervised learning approach in which you cluster your data based on into different levels. So Um, so so what the way random forests work, they only see the ordering of the data. They only focus on the ordering of the data. They don't see they don't see if they aren't able to capture if the data is linear or non-linear. So only that matters is the ordering. So we use something called rank correlation to convert our data uh, to convert our data. So on the left, you can see if this is your original data um, where your data set is nonlinear. After rank correlation, it becomes almost linear. So basically, you what you do is you basically plot the order of the samples in rank correlation. So let's say like for so if you plot the order of the order of these data points, then it will look like a linear line in this case. So that is something that is used for that is used in dendrograms. Like, so we'll use rank correlation for finding these correlations among the features. So so here I've written the code for finding the rank correlation between all the columns or features in our data set. And if you look at this plot now, uh, as you move right on this horizontal axis, it tells you how similar columns are, like two columns are. So so the rightmost columns are the ones that are most similar. So you can see like these values, FI base model, FI model, D desk. These are the most. These are like very similar like features. And then there are other features like sale year and sale elapsed, and then other and some features like coupler system, hydraulics flow, browser tracks. These features are very much related. So what we can do is we can try removing one feature from each of these groups and see if we get a better model. Uh, Now this is so this is the code where I do this, and I remove like I start removing one of the I start removing each feature one by one and see if I'm getting and see what R squared score I'm getting. And you can see that the R squared score is pretty similar in this case, like it hovers around 0.88, 0.89. So uh, so we can safely like drop uh, one of these features from these groups. So that's what I do here. Like I drop sale here, I drop FI base model and browser tracks, and I mean, we can see that we get a score of which is like pretty similar to what we were getting like in our previous models. So and after dropping these columns, I remember like we only selected a subset of samples for doing model interpretation. Now I run this on my full data set, and you can see that we're getting like a pretty good score here. Like I'm getting 96%, sorry, a 0.96 R squared on my training data, and uh, 0.9 R squared on my validation set. So so basically we now have a very a much simpler model, and which gives a better score. So you can use these techniques, this technique to basically find relations between the data. And what it helps sometimes is with regards to feature importance. So let's say if I go to my previous examples here, uh, yeah, let's say we'll look shortly that year made and and sale elapsed, these two variables are related. Now what happens is if you have uh, like if you have features that have interaction with each other, or like collinear, then they kind of like reduce the feature importance of the features. So like uh, so you could say that sale elapsed is reducing the impact that year made could have uh, made on the final price, on the price prediction. So so removing some of these redundant features or like similar features helps you in uh, in making our model simpler, and sometimes it leads to getting a better score. Um, so next, uh, we'll look at something called partial dependence plots. Now, this is a very powerful technique to understand our data using the model, and this helps us finding the relationship between the target variable and and the features that we have. So here I'm using a library called PDB box for getting these partial dependence plots. And similarly, I select a subset of observations from my data set, and 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 yeah, I'm using the model that I trained on the one hot encoded features. This basically is the feature importance on those one hot encoded features. So you can see that the enclosure erupts with AC has the highest feature importance. You can also see year made is also here. Now, if you plot, do a scatter plot of year made, uh, uh, of year made, sale elapsed, and sale elapsed, you can see that there are uh, there are a bunch of values around the year 1000, which is basically, I think these values uh, are missing data. So basically, they don't have information regarding when these equipments were made. So for analysis, I'll not consider these values, and we'll only focus on values that are present here. So that's what I do here. I only look equipments that have been made after 1930. And now if I plot the relationship between the year made and the sale price, well, in general, we would expect a straight linear line. I mean, a linear plot. That is because, you know, as the year of manufacture becomes more recent, or like as the year of manufacture increases, you'd expect inflation to make the equipments more expensive. Also, newer models tend to be more expensive, so you would expect a straight line. But you can see that there's a dip here, like between 1990 and the year 2000. So in that, so so here is what why univariate plots can sometimes be very misleading. Like uh, it might lead you to think that okay, between 1990 and 2000, maybe the year made is not impacting sale price the way it should. But but what might be the case is there might be a lot of other factors that might be affecting it or impacting it. Like there could be a recession going on during that time that made this that made the sale price to go low. Or there might be there might be a lot of competitors that came up during this time who so I mean, basically you had a demand and supply issue. So there was a lot of supply, so you had to reduce the sale price. So there could be a bunch of things going on here. uh, uh, so what we can do here is, so our intuition says that as the year made increases, the sale price should also increase. So what we can do here is we'll see. So let's say I want to see if I may if there was a particular equipment that I sold to the same person and at the same auction. Like I keep everything constant and see uh, if that particular equipment, if I sold it in 1980 and if I sold it in 1990, would have different price. So so basically I'm keeping all other things constant and just changing the value of the year and seeing if that prediction, if I what kind of prediction I get for my price. So my intuition is that it should increase because as I said, because of inflation and because newer models tend to be more expensive. So we can do this using like partial dependence plots. So basically what I can do is So what we can do is, so this is very similar to how we did the feature importance plots. Basically, what we can do here is, for the year made column, we set everything as constant, like the year as constant. So basically, in this case, I set the year to be 1960 for all the rows I have in my data set, and then see what prediction I'm getting. So basically, what I'm trying to do is I'm keeping everything constant except the year made, and seeing if if I sell a particular equipment under the same conditions, but only change the year in which they were made, then does it affect my the price? And after doing this kind of analysis, I see that I get like a general increasing trend in my price that I was expecting. Like as the number of as the year increases, the price also increases, which is given by this dark like this dark line. And these faint blue lines, these are basically my different observations. So you can see that I selected 1,000 observations here and did analysis on that. And so these blue lines say that at different points of time, like at different years, what would be the value of for this particular row? Like what would be the price for this particular row? Now this looks a bit messy, and if we try to cluster them and see if, we kind of trying to see if like some of these items they have increase in price or decrease in price together, we can cluster them and see that there are like kind of different types of clusters in this data. And it's interesting to see that there are some equipments that whose price has flattened out like after 1990. And this is an interesting thing that depending on your use case, it's worth investigating that why some equipments why the price for some equipment stagnated. And I mean, obviously the next step would be to talk to your client or to a domain expert and see if like these things make sense. um, Similarly, I mentioned that there is a relationship between sale elapsed and year made. So basically, sale elapsed tells you. So basically, we are selling auctioning of heavy equipment. So they were sold at some point of time in the past. So the sale elapsed tells how how far in the past was that item sold, like to an individual. So so we would accept. So this partial dependence plot, it's called it's called an interaction plot. So there are two variables that I'm considering: the sale elapsed and the year made, and I'm trying to see what the relationship is with price. So here in the top right, you can see this is like kind of what we would expect. So uh, as the sale elapsed, time increases, the price decreases. So basically these items were sold way back in the past, while this is the plot we just did in the previous section, with just the price with respect to year made, which increases. And now you get a very interesting plot of sale elapsed and year made with respect to the price. So so we would expect that the items that the equipments that are more recent, they to have the highest price. So this will be so this these fluorescent values, they show that indeed like these items have the highest price. And the contour lines, you can see they are kind of a bit weird. You'd expect them to be kind of linear, but again, we have taken the log of our price, so they look a little bit they don't look linear. At the same time, there's a bunch of interaction going on in this data set, so that is affecting the price as well. um, Similarly, we can do such kind of such an analysis for the variable for the categorical variable enclosure. So we saw that this variable was an important variable in our in our analysis enclosure EROPs with AC. And basically what this variable means is that uh, so this data set is on bulldozers, right? So it says that this bulldozer has an enclosure, so basically it supports air conditioning. So and that's why you see a higher price for these bulldozers which have air conditioning, and the ones without an air conditioning and the ones with open top, they have a lower price. um, so yeah, I mean, partial dependence plots, they help you like in finding the real relationship of the features with the with your target variable. And yeah, and they are much less like misleading than univariate plots. um, so yeah, finally what we do is like we saw I mean, based on our analysis, we can see that the sale year and year made can be grouped together to something called age. Like we can engineer a new variable called age from sale year and year made, and then retrain our model to give a new feature importance plot in which the age now has the maximum feature importance. So yeah, I mean, this shows that we can do some analysis using feature importance plots to you know to improve our model and to get, it sometimes helps in it actually helps a lot in feature engineering and finding uh, relationship between variables and and your target variable. Now this last section I'd like to cover tree interpreter. Now this is specific to random forests. um, Random forests, or I think also it should be applicable to boosting algorithms. So now tree interpreter is one thing that is very important in businesses and in real life. So let's try to understand the motivation behind it. So let's say we are an insurance company, and somebody rings us up, and we give them a quote, and they say, "Oh, that's $500 more than last year." But why? So in general, we have made a prediction from some model, and somebody asks the reason behind the prediction. This is where we use this method called tree interpreter. So what tree interpreter does is it allows us to select a particular row and pass in our random forest model, and it gives back three values. The first is prediction. So the prediction is basically the predicted sale price using our random forest for that particular row. The bias is the average sale price across our whole like training data set, and the contributions is the contributions tells us the uh, how much how much change in the bias is the prediction. I mean, how much change in the bias the value of this particular feature making. Like uh, it's basically the what is the contribution of this feature in reducing or increasing the predicted price with respect to the bias, which is basically the average sale price across the whole data set. We use something called tree interpreter here. It's a library um, that you can use, and and we select a row here, one of the rows from our validation set. Um, and now we calculate the three values that I mentioned: the prediction, the bias, and the contributions. And we can see that our prediction for this particular row was 9.33, while the bias was 10.10. And if we try to visualize or try to see what each feature contributes to, we can see how each feature contributes to this value. So for example, like the product size being mini, led to a reduction of price in minus 0.54, while the year made being 1999 led to increase in the predicted price, like like by 0.09. And this is with respect to the bias that we get, that is like 10.1. um okay, we still have 5 minutes, so I can go over this example to make this more clear. um yeah, so basically, let's say we divide, uh we have the here the value says the is the bias. So it tells us, so this is the average value of sale price across our whole data set. Now the coupler system being zero point 0.5, so if the coupler system is less than 0.5, then uh, then the then the value becomes, the sale price value becomes 10.345. And at the same time, if the enclosure is less than 2, then we reach here, uh, our value becomes 9.955. So if you look at the example that we had, um, I think this was the model ID, which is 665. And so and I think the enclosure, let's see what's the enclosure was. I think it was 0.5 or something. um yeah, I mean, you can like and this is one sample tree. Like you can follow this tree and see how the values for different features is affecting the final, predicted sale price. And this, of course, like, now you'll have to average it over all the different trees in your random forest, and then you'll get the final, these three values: the prediction, the bias, and the contributions. uh, Now, these changes can also be represented in the form of a waterfall chart, which is very popular in management consulting and business. So here on the left, you can see this tall blue bar. It's the this is the bias. So this is basically the average average sale price over your whole training data set. And because because the coupler was less than zero point 0.5, it led to an increase in 0.15. Because the enclosure was less than 2, the bias reduced by 0.395, and so on. And so you reach this final price for this row based on the contributions, based on these contributions from these three variables. So now if someone asks how come this particular auction's prediction was this particular price, we can answer because these three things had these three impacts. So this kind of like makes your tree very much interpretable. And um, I mean, it's easy to like convince your manager or the business like why some kind of why your model is making these kind of predictions. Now, like, of course, like these kind of analysis, this won't help you like win Kaggle competitions, because all it matters there is like accuracy. but but these things are very important, like, from the point of understanding your data, or from a business perspective, or even like in a real job where you have to convince like your the business or your client why you're using a particular model and why is it giving such insights. um, so lastly, yeah, I mean, I have listed the resources here by this is the machine learning course that I mentioned at the beginning of the talk. And this is another book that you can go through, that covers a lot of the things in details. And then there are other model interpretation packages like Lime and SHAP, which are little which treat these different model interpretation like techniques in a different way. But yeah, you can feel free to take a look at them. So that's all. Questions?
Thank you very much. And yeah, we're opening. So if anyone has any questions, please ask. And in the meantime, I'm going to send a quick survey link in the Zoom chat for if anyone would want to fill that out. Yeah, feel free to ask any questions. And I guess I can start because I had a question about when you shuffled the feature data for that in the beginning. I guess I didn't understand so much the, why you wanted to shuffle the feature data or what that would tell you. So are you comparing, are you trying to decide whether it's the, big statistics for that feature data that are important or the actual sort of ordering in the data or, row by row?
Yeah, I mean the row by row. So if you shuffle the data, you're basically breaking the relationship between the feature and the variable, right? Like the predict what you're trying to predict.
Mm-hmm.
So you're trying to kind of find that if I destroy this variable, then what impact will it have on my final prediction?
Okay.
So if you randomly shuffle it, and it makes a very huge impact on your predictions or like your accuracy or RMSE, then you realize, okay, this feature is very important, so I should assign it a very high importance value. So I think that yeah, did that make it clear, like why
Yeah,
I'm shuffling? Yeah, yeah.
that made it clear. And then, so what's I guess, the advantage for shuffling instead of like dropping that data?
Yeah. So if you drop, so the problem with dropping is that if you drop that column, then you'll have to retrain your random forest, right, on the selected features.
Yeah. Okay.
So that is something that you can avoid if you do like this kind of technique. So you don't have to like retrain your random forest again and again.
Okay.
Yeah.
Then I guess I had one more question. So when you, I think it was above this, you would kind of reselect features. I forget exactly how, but essentially you minimize, the features that you want to look at, the cutoff, the 0.005.
Mhm.
So, assuming you had like many, many features and you kept repeating this process where you would retrain the model on your new features and then kind of discard the ones you think are not as useful. I guess, how do you know, your stopping point sort of, or where is the golden medium? And
Yeah, that's a good question. I mean, this is like kind of a value like 0.005. It worked like it kind of worked for this particular data set or like particular problem. Yeah, you'll have to see where like this tail starts. I mean, where this where this actually the feature importance starts decreasing, and then you can start dropping them probably one by one and retrain your model. You basically have to stop at a point where you see that your performance is deteriorate, like it's basically going it's going like really worse. So yeah, I mean, there is no set principle behind this, so this has to be done on a trial and error basis.
thanks.
And yeah, I'll share the link to the I'll share the link to this like notebook on Google Colab or GitHub soon. I'll share it soon.
Okay, awesome.
Yeah.
Yeah. And just as a general comment, I really liked all the various ways you visualized the, relationships between features. And
Mhm.
I think all these plots are really useful.
Thanks.
Thank you so much for teaching, Sheel. We really appreciate it. This is an awesome lecture. Thank you for being a part of our boot camp today. If y'all don't have any other questions for him, then we have one more class left today that we would love to have y'all join us for, and that link is on the events page. And also filling out the survey would be really helpful to us so we know what to do for next time.
Right, thank you.
Thank y'all so much.